Spin-orbit interaction was much larger than the exchange interaction. So I can talk about only spin-orbit interaction and treat exchange interaction as a perturbation. When I came to the S level, I had no spin-orbit interaction. I can talk about only exchange interaction. But when both became comparable, which is here, I cannot talk about only the spin-orbit or exchange. I have to treat both of them on equal footing. And if you do that, then you get exactly the same result. You can calculate these atomic physics and you'll get, there are horrendous number of multipliers, calculate all the multipliers and their intensities, and you get a perfect description. So you see how all the atomic interactions you are getting out from these measurements. The other aspect of photoelectron spectroscopy, which is also very important, is the fact that this binding energy of these characteristic, let's say vanadium 2p level, actually depends on the oxidation state of the vanadium. That's because every binding energy is dependent on how many electrons are there at the vanadium site. If I go from vanadium metal, which is here, it has certain number 3 d electrons and 2 s electrons. If I go to vanadium monoxide, it has 3 d electron and no s electron. And successive ones, V2O3, it has 2 d electrons, no s electron, 1 d electron, no s electron, and no d electron, no s electron. And the binding energy, which we call the chemical shift, with reference to the metal, keeps increasing. Each of these tick is 1 electron volt. Sorry that it's not marked. And you can see that approximately by 1 electron volt I shift for every change in the oxidation state. Not only with the oxidation state, keeping the same oxidation state, it senses the electronegativity of the partner element. So if I look at manganese iodide, bromide, chloride, and fluoride, it continuously, that peak shifts. So by looking at the peak position, I can find out not only the chemical composition, that means which element, because 4 levels are characteristic of the element, precise measurement of that peak energy and referencing it to the metal or element of it, I know what the shift has been, and that shift tells me in which oxidation state it is in, or which kind of chemical environment it is in. That is the reason originally when Kai Sigman discovered this technique, he called it ESCA, electron spectroscopy for chemical analysis, not elemental analysis. Elemental analysis, of course you can do, but you can also say that element in which oxidation state it is in. And when you look at even the outer orbital, like coming back to the terbium, 4f8, now 4f8 means there are 7 up electrons and 1 down electron in the ground state, giving you the 7f6, heptate f6 configuration, and that you can knock out this electron or you can knock out one of these electrons. If you knock out this electron, then you end up with a 4f7 up state, so the final state can be an octet s state, or if you knock out one of these electrons, then there are many possibilities, and there's an all sextet states you can see. It can be sextet P, I, D, G, H, and F, and you get signature of all of them in the main peak. Some are really degenerate, so they, for example, all these together give you one peak, this peak, that peak, and that peak. So there's a tremendously rich information contained in there. There's also ligand field effects and etc. that I'm not going to. Let me see what am I going to try to talk about it. There's a symbol of green there. I don't know why outer valence levels are there. Because I have the few minutes left, I just want to cover. Okay, I'll not cover everything. I have no syllabus to complete and you have no exams to give. Okay, so let's not worry about it. I just pointed 1 or 2 more things and then complete. So far, I have said that the intensity is proportional to the density of states, proportional to the number of photons coming in, and also I have said that there is a matrix element effect. And we use this matrix element effect very effectively. Because the matrix element effect, so the probability, so the number of electrons coming out at any given kinetic energy is proportional to there's this matrix element, probability of emission of an electron, and the number of states, which is the density of states. That probability is written as this MIF square. This MIF is the matrix element of the dipole operator that Shanta talked about this morning from the initial state to the final state. This quantity depends very strongly on the initial state I as well as on the final state F. If only MIF would be constant, the intensity would be proportional to density of states, but it is not at all constant. It depends very drastically the nature of I and nature of F. Now, given the nature of I, nature of F is fixed because given an initial state, which final state you go to is fixed by the energy conservation. But you can change that by changing the photon energy, again by energy conservation. So if I change the photon energy, my MIF squared would change very drastically because even for the same initial state, F is changing. And keeping the same photon energy or going to the same final state, if I choose to look at different I state, the energy state, different binding energy state, MIF square would change very drastically because then the I is changing. So both are used very extensively to understand what kind of level I am looking at. For example, to give you some idea, let us take photon energy of 21 eV and 800 eV. The copper 3D orbital has an MIF square is in the order of 7.5 for 21 electron volt, but only 0.03 for 800 electron volt. That means keeping the same I, when I'm changing the F, changes, the MIF square changes by 2 orders of magnitude. Very strong change. So that means when I don't know what state I'm looking at, by changing the photon energy, I can figure out what kind of state I'm looking at. Because the way it's changing. For example, if I have copper oxide, and the valence band, both copper D and oxygen P are mixed together, and I've got this big blob of a spectrum, I want to know which part is more oxygen P, which part is more copper D. All that I do is, once I record the spectrum with 21 eV, where you see that oxygen P is a little higher intensity than that, and then I go to 800 eV, though this has decreased, but this has decreased even more, here I get dominated by copper. So the spectrum at 800 eV would be dominated by copper D contribution, but at 21 eV it will be more dominated by oxygen D contribution. Therefore, looking at the way the intensity is changing, I'll be able to say this part of the spectrum is coming more from oxygen P state, this part from copper D state. There are many other tricks of changing the photon energy, dependent cross sections that I'll not be talking about. These are called Cooper minimum, resonant photon emission, where here I am talking about changes of 100 eV. Here for a few tens of eV change, I can change the cross section by an order of magnitude. This is another technique where by changing the photon energy at some threshold values, by a couple of electron volt, I can change the cross section by an order of magnitude. And that gives us tremendous ability to extract the partial density of states by enhancing the cross section of a particular character by tenfold compared to the others. And this is the last thing that I'll explain to you, because this is the one that will tell you how delta U and T are extracted from electron spectroscopy, because that's what I promised to do. So I'll just take another 5 minutes. Is it okay? Are you guys very hungry? You can't be more hungry than I am. I'm doing all the work. And I am hungry. So I'll finish it quickly. Okay. So let's look at the core level. We talked about all this. You know everything about core levels. Or you know what would happen if we look at copper 2p. Copper 2p, let me say the exchange interaction is very weak. So how many peaks do you expect to see in copper 2p? Core level? It's all written here. How many peaks should we get? Spin-orbit interaction gives me 2 peaks, right? Just like here. So copper oxide, let's look at some copper oxides, let's look at the thing. What we see is 4 peaks. And I have an approximate separation that these are all related to 2p3 these are all related to 2p half. For some reason, each of the spin-orbit thing has a partner, and we call them the satellite. This is the I think this is copper chloride. So it's not only an oxide. This is copper chloride. This is strontium copper oxide. This is intermediate copper oxide. You take CO, anything you take. Copper 2+ state, you will have these two peaks. But if you take copper 1+ state, you will not have this. You will have only one peak and one peak. Copper 1+ state is a D10 system. Copper 2+ state is a D9 system. But it is not because of exchange interaction. Because we can calculate the exchange interaction. That all comes at very small energy. So where is this coming from? And that is the one that I'll explain to you and close the talk. So that is called the main peak, and this part we call the satellite. So you have to understand the origin of this satellite. For that, we need something called sudden approximation. I'll not go into that because time is short, but I'll still take this very simple model to explain to you what is happening. Again, it's all a trick of that EF of n-1. N-1 is -1 is from the 2p core level. But the final state will be defined not only by that hole, but if some rearrangement takes place within the valence level, that also will change the energy of the final state. And it is a particular kind of rearrangement that takes place which is responsible for that satellite. And I'll tell you what that rearrangement is. Since I'm talking about copper 2+, which is a D9, and oxygen is P6, in terms of electrons, allow me to think in terms of holes. There is no hole in the oxygen, so 0 hole. And there is 1 hole in the copper, so 1 hole. And that is what I am writing down here, D1, P0. There is copper level, there are 1 hole, and oxygen has no hole. But remember hopping we talked about. This hole can hop back and forth with oxygen, which is the same as the electron hopping back and forth. If this hole hops to the oxygen side, I'll have 1 hole in the oxygen and no hole in the copper. The energy difference between this level and that level is exactly the charge transfer energy that I've already defined for you earlier. So that's that. And this hopping strength, if it is T, then I get a bonding and an antibonding. This splitting is given by essentially twice T. It's also dependent on a little bit of delta. And there is this core level 2p with no hole. That's why 2p0. Because I'm writing only holes. Now I cause a photoemission and it becomes 2p1. Now this 2p1, there's a hole here and there's a hole here. These two holes will repel each other by Coulomb interaction. That Coulomb interaction I write it as UDC, D hole and core hole. And that energy is this much, so this one gets pushed up by that much. Here the hole is lying at the P level and the core hole is at the copper level, so they don't interact. So that energy remains exactly where it was. So now the charge transfer energy, here it was delta, but now the charge transfer energy becomes delta plus UDC. Correct? And I get a new bonding level and anti-bonding level. And there is a certain probability that the system, the F final state, could be here or could be here. Here we start with here because I am in the ground state. I have given it enough energy. But after suddenly pulling the electron out, this system, when it has to from here, go here, it has a choice of going either there or going either there. And the probability of its going from here to there or here to there is nothing but the overlap of this wave function with that wave function and this wave function with that wave function. That's a statement of sudden approximation that I have not shown, which was in the previous slide. So the probability with which it will go here, I can calculate by that overlap, probability, that overlap. So I'll get 2 peaks depending on whether it goes here or there. The 2 peaks will be separated by this separation because the energy difference between the two states, final state is exactly this, and the intensity would be proportional to this probability and that probability, which I can calculate. But you see, this probability as well, this energy difference will depend on the delta plus UDC, and the energy difference will also depend on T. So in detail, trying to simulate the spectrum, getting the intensity and the energy separation right, I'll get an estimate of delta, UDC, and T. In fact, this is a Mickey Mouse problem because essentially it's a one electron problem because I have only one hole here. And this second hole that I put in doesn't have a dynamics, meaning it cannot jump to there because it's a deep core hole, so it provides only a DC shift. So this can be solved in closed form. And that solution is given over here. The delta E, it's a very simple calculation, tight binding model. You take bonding, anti-bonding splitting, that is exactly given by this much. And the intensity ratio of these two is given by the tan square theta minus phi, where sin square theta is defined as this way, sin square phi is defined that way. And you can see these are dependent on these parameters, delta, UDC, and PP. Forget the TPP, this is for a complication we are taking, and the T, which is the interaction string between here and there. When that happens, by fitting the spectrum with this model, I get the values of delta, UDC, and T. That's how we determine T, delta, and UDC. The nomenclature is, we call this well-screened state, and that is poorly screened state. It's very easy to understand why. Because in this state, you see that this has more D0P1 character, and this has more D1P0 character. Now, D0P1 character means what? The hole is residing at the P level. Why? Because I created a hole here. In order to charge neutralize it, the hole that I had at the D level went away and went to the oxygen side. And so, it's equivalent to, I created a hole here, an electron from oxygen came to this side to screen out this hole. Right? And if that process doesn't happen, then you are there. That's why that's a high energy state. If the electron didn't come, it didn't screen the hole. So that's a poorly screened state. And this is a well screened state. That's why this has lower energy. So this is essentially a process of screening, and there are two channels available. One channel represents a good screening, the other poor screening, and there's a possible probability of ending up with both, and that is exactly what you get, and you can do the calculation, and the calculation will reproduce these results very well. I'm showing you some quick examples after this. Out of this, these are the well-screened state, and these are the poorly screened state, and there's just a spin-orbit replica of that. And there are more complications because you can see that actually this state is not just one level. This is the multiplet interaction of the hole in the P level and the hole in the D level. The exchange interaction that I talked about gives rise to many, many multiplets, and those multiplets is the one that gives it structure. But this peak corresponds to a hole in the 4 level, but no hole in the copper D level. So that has no multiplet structure, so it's nice and sharp. So you can then set up complicated Hamiltonians where this is the energy of the D level, this is the energy of the P level, and this is the energy of the core level, and this hopping part. So this is the tight binding part that we had talked about before. Well, this is also the tight binding part between the oxygen P's, because I said building of the minimal model, we had realized that oxygen P interaction is also important. That's the tight binding part. Along with that, you throw in the complicated Coulomb interaction part that you have been talking about. It looks like that, you don't have to worry about it, but one can write down. This is a Coulomb interaction, the core hole at the D level. You also bring in the Coulomb interaction within the D level with full multiplets. That's why it looks so complicated. And then you can bring in also the spin-orbit interaction, and that's your Hamiltonian that you need to use. And then you take very complicated systems where you have open shell for everything. This is a nickel 2+. These are all nickel 2+. NiO, PrT NiO4, Y2 Ba NiO5, and Lu2 Ba NiO5. What was being done? This is a 3-dimensional oxide, it's a 2-dimensional, it's a 1-dimensional, and it's a 0-dimensional. And how the structure changes, this is a 2p3½ satellite replica, 2p½ satellite replica. And there's a solid line overlaid on it, which is the calculation. And you can see how good the description is when you take all these interactions into account, and that allows you to extract reliable estimates of T, U, delta, etc. That is all that I wanted to point out to you. Let us stop at that, I don't want to complicate your life any further. It's complicated enough already. And let me end thanking you, because this is my last talk. I really thank you for being patient, for at least keeping your eyes open. I've been watching, and for being here. Thank you. But no, it was always before.